Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on Java native interface and look at an important topic about how to create a unsafe class. So what is an unsafe class? So an unsafe class usually is a class that allows us accessing and manipulating off-heap memory directly. So basically this is a memory that is not on the Java heap, it's on the native heap, and we directly access it without the intervention of the JVM. And sometimes this is a good thing to have, because then this memory is not subject to automatic garbage collection. The downside is that now we have to manage this memory manually, and it might not be a good thing, but I mean, if we need a good performance, then sometimes it's good to be able to directly or manually manage the memory ourselves, right? So what are the methods that an unsafe class should provide us? And obviously it should give us the ability to allocate memory in terms of how many bytes of memory we want to allocate. So bytes of memory to allocate. And we know that in C++, a char type is 1 byte. So when we want to allocate some number of bytes contiguously in the memory, we use a char array of bytes. We use the new operator in C++ or malloc in C. And then this allocates memory on the native heap, and then gives us a pointer to that memory, right? And then a pointer has a value which is 64-bit, obviously on a 64-bit platform, or 32-bit on a 32-bit platform. Here I'm assuming it's a 64-bit. And then when we allocate in C++, it gives us a pointer 64-bit. Then we have to return a memory address from this allocate memory, so that we know, or we have the address to that allocated memory on the C heap, on the C++ heap. And a 64-bit address is basically a long type in Java. Therefore, when we work with the memory address, we use a long type, which is a 64-bit, right? So working with long integers. Obviously, if we can allocate the memory, we have to be able to free it or delete it. We know that the new operator for arrays has a delete array operator. And then we have to pass in the address that points to the beginning of this chunk of memory of this array. And then the unsafe class should give us the ability to put a byte type, a short type, an int type, or a long type. These are integer types at any address point inside this allocated memory, right? So we pass the address that we want to put that integer from that address, and then also the value of the byte, short, int, or long. Similarly, for the floating points, put float, put double, we pass in the address and the actual value that we want to put in that address. And then we should be able to also retrieve the values, the primitives that we put in that addresses. So get byte, we pass in the address that we want to retrieve a byte from that address, and then get short, get int, get long, get float, get double. So in all these methods, we pass in an address, a 64-bit long address, and then it returns, it reads the bytes of the memory beginning from that address, and then gives us back the value that corresponds to byte, short, int, long, float, and double. And to refresh your memory, byte is 1 byte, short in Java is 2 bytes, int is 4 bytes, long is 8 bytes, float is 4 bytes, and double is 8 bytes. The reason this is important to remember, because now because when we allocate the memory, it gives us a pointer to the beginning of that memory block, which we typically call it a base pointer, which points to the beginning of the block of the array, right? And then if we call, for example, put byte, and then when we added the pointer that points to the next block or the next available memory is a base pointer plus 1. However, if we use put int is 4 bytes, so the next available memory slot is base pointer plus 4. Similarly, for long, it's 8 bytes. So when we use put long, the next available memory is the base pointer plus 8. So, I mean, an unsafe class helps us directly work with raw pointers, right? It gives us a raw pointer in the form of a 64-bit integer, which is exactly what the raw pointer is. And then having a contiguous block of memory increases locality and potentially reduces cache misses. What this means is that if you are familiar with the struct construct in C++, if I create a struct usually has a flat memory layout, which means that if I have a struct and define an int array in it and then a double array, these are allocated next to each other. However, in a Java class, if I have a field which is an int array and another field which is a double array, remember, int array and a double array, primitive arrays in Java are objects. So basically, when I have an int array, it's actually a pointer or a reference type to where the actual array of integers is located inside the Java heap. Basically, what I mean is that if inside the Java class I define an int array and a double array, these are not guaranteed to be laid out in the Java heap next to each other. However, in a flat memory structure like a struct in C++, if we have a double array and int array, they are basically next to each other, which is good because that means the locality is high, and therefore when the CPU fetches an instruction, let's say we get access to the int array, then the double array might be cached, therefore it increases the performance to some extent. So sometimes we want to take advantage of this. If I have a class in Java that has a lot of different arrays which we use as buffers, then maybe we don't want to have a lot of different references, and then we just want to have a big chunk of memory that is completely next to each other, and then we want to manually operate with it. So we cannot use a unsafe class to allocate something on the stack, on the C++ stack, because again, when we use JNI, a native call to go to native environment and allocate the memory, as soon as we return whatever is on the C stack, because it's returning from a native call, which is a native function, a C++ function. As soon as we get out of that function, anything that is created on the stack is destroyed, right? So when JNI call returns, all the stuff on the C++ stack is destroyed. I mean, there are ways, for example, if we declare some variable inside a function in C++ as a static function, then it's not really stored on the stack anymore. It's somewhere else, and then even when the function returns, that static variable is still alive. But that's not really useful in this case. All right. So let's head to Eclipse and let's look at how we can quickly write our own unsafe class and use it to work with raw pointers in Java and manage our memory, which has very high locality when we are dealing with arrays. So here I've created a new package, test29. And usually when we create an unsafe class, we put it in a MISC package. So my unsafe class that I have created is inside test29.misc package, and MISC stands for miscellaneous stuff, right? So test20 my unsafe class is inside test29.misc package. All right. Now, obviously, this is going to have a lot of native calls, so we have to load the dynamic library that actually does the native calls for us. And then typically we write this in form of a singleton. So this is the singleton pattern, and the name of the field, the name of the instance. So this is the singleton instance. Is always the unsafe, right? So the field, remember, the name is the unsafe. So private static unsafe, the unsafe, new unsafe, and obviously the constructor is private. So private constructor, and then we have a method public static unsafe get unsafe, and we return the unsafe, right? And we can do lazy initialization, but this is an eager initialization. So this is eager initialization, which means this field gets initialized as soon as we define it. but we could initially have it null. If someone requests it, then we can initialize it. But usually when we design the JDK, because this is usually the unsafe class is related to the internals, right? It's an internal, it's intended for internal use. So we don't want other developers use it. So typically what we do, we put a roadblock on it, which basically we ask JVM to check the class loader for the class that is requesting this call, get unsafe. And if it's not, so if it's not a system class loader or a bootstrap class loader, we throw an exception, right? Throw exception. So that's typically what we do in the JDK, because we don't want other developers that are outside the JDK development team use the unsafe class, right? But there are ways, and we'll discuss how to actually access the unsafe class that is inside the JDK, even though there is this kind of roadblock and checking for security. But here I'm just writing my own unsafe class. It's a singleton, and the very first thing that we need to have methods to allow us to allocate some bytes of memory, right? And then it returns a long integer, which is basically returns the address. So allocate some number of bytes of memory, and then return the pointer or the address, the memory address, to the beginning of the memory block. As I mentioned, this is called the base pointer. All right, and we need to also be able to free the memory, and we pass in the pointer to the beginning of the memory block. And so then we can have methods that help us deal with primitives. We can have a put int method. It doesn't return anything. It takes the address at which we want to put this integer and the integer value, and then get int. This takes the address that we want to retrieve an integer from that, and it gives us an integer. Similarly, for double, byte, short, we can have any types of these. But for now, I'm going to just show you these two. So once we have this, we write quickly this unsafe class, we select it, run our Java H tool, and it creates the header file, which I have already done it. It's in the test29 misc unsafe.h, and allocate memory, free memory, put int, get int, put double, and then get double. And these are all, I define them as a static methods. So we get a J-class reference, and then we go to our source folder and create a CPP file. I called it unsafe.cpp, and then we include the header file, and I'm also including the IO stream to print out some stuff on the console. And then we copy and paste these prototypes in the CPP file, and then we provide implementation. So how do we allocate memory? So basically, this allocate memory takes some number of bytes, and again, a byte is represented by char type in C++. So we say char pointer new char array bytes. So this creates a byte array on a native heap and returns a pointer to it. All right. So we allocate memory on the heap, and then we get a pointer, and I'm doing a stdcout allocating this number of bytes of native memory address, native memory at this address. So this pointer is a 64-bit pointer, right? It's a memory address, but because it's a char star, it's a char type, if I write it to the console directly, it's not going to show anything. So I'm converting it to a J-long pointer. So I'm telling it, when you put it to the console, convert it to an integer type pointer. In order to just see the value, the actual value. And it's obviously pointer types are always pushed out to the console as a hex. So pointer types, when we use stdcout, this operator, they pushed as hex numbers. All right. So I'm just, and then this pointer type, and now when I send it back to Java. In Java, we don't have a long pointer, right? We don't have long start. We just have a long integer. So I have to just convert it to a 64-bit integer. So this pointer is a char star pointer, but it doesn't matter. Remember, type conversion of a pointer doesn't change its value. It's just the way we interpret that, or the compiler interprets that value. So we're saying that, okay, now convert it to a JLong integer and send it to Java. And then it's a 64-bit int, which is the case for the pointer, right? Now, similarly for free memory, we're sending the JLong or the long integer address, which is a 64-bit. Remember, JLong is guaranteed to be 64-bit, which we are using on a 64-bit platform for pointers, memory addresses. And then I take this JLong and I know that it's representing a byte array or a char array. So I convert it to a char star pointer. So now it's interpreted as a char pointer. And then I'm doing a delete on this pointer, which is pointing to this actual char array or a byte array. And it's correctly deleting it, right? Remember, we have to do this conversion because the original array that was allocated is a char array or a byte array. And I'm writing to the console that I'm freeing memory at this address. And again, this address is long integer. I convert it to a long pointer. I just want to see the hex representation, right? So that I convert it to the long pointer, and pointers are pushed to the stdc out as a hex representation. And we delete this pointer. Remember to use delete array. So this is array delete. All right. Not just the ordinary delete. This is the array delete because we allocated an array of bytes. Obviously, we can then compile, build this. All right. The build is successful. We copy and paste the dynamic library in Java, and then go back. I created a class called test unsafe, right? And let's start with test one. In test one, this is a practice of how we can actually access any unsafe class. So I know that on the class path, my unsafe class is in the test29 package.misc package.unsafe. This is a fully qualified name of the class. So fully qualified name of the class. And this is very similar to what we do in C++ with JNI. In C++, we say that JVM find class, and then we have this class path description, right? This is similar to saying that class for name, and we have to specify the class path description. But in C++, the class path description, the separation is a slash. In Java, the separation is dot, right? Packages are represented by this dot. So we search for this class, unsafe class, on our class path, and then we know that this is a singleton. So the actual instance is a field that is called the unsafe. So we say that class, this is a meta information, get declared field, the unsafe, and it's always a private. So it's private field. What we do then is we set accessible to true, and we discuss this in our lectures when we talked about the similarity between JNI and Reflection API. In Reflection API, there are some extra security checks. So if it's a private field, we cannot directly access it, but we can set accessible to true, and this allows us to access this private field. And then we say field.get, and this is a static field, unsafe, so we don't have any special instance of the object to pass in through. And then we cast it to the unsafe. And now that we have unsafe, we are off to the races. So we are off to the races as working with, so basically enjoying working with the unsafe class. All right. So here, this unsafe is my own unsafe, the unsafe that I wrote here. But later on, we look at how to actually use the unsafe class inside the JDK. But this is exactly the way you would access the unsafe class inside the JDK. So if I run test one and look at this unsafe instance and look at its class, it should be fine. So yes, I can correctly access this field, the unsafe here, which is a private static field. and because I initialized it, I could actually declare it as a final. That's fine. So in test 2, what I'm doing, I'm simply allocating and deallocating some memory. So unsafe.allocate memory, and I'm telling it to allocate 10 bytes on the native heap, right? And it returns a long integer, which is the memory, which is supposed to be the memory address, the 64-bit address that is pointing to the beginning of this memory block. That's why I call it pointer or base pointer. Now I'm doing so there is a stdc out that prints out the information. I'm also converting this pointer into a hex representation, long to hex string, and doing a printf to see that this is correctly returning back the memory address. And then I say unsafe.free memory and pass in the pointer. Remember, this pointer should point to the beginning of the array, to the beginning of the memory block or the array. All right, so let's run test 2. So we are allocating 10 bytes of native memory at this address. This is this pointer, char pointer, that I converted to JLong pointer just because I wanted to see its value. And then pointers type are always represented as a hex, a number in the standard output, right? And as you can see, when I return back this address as a long integer, it's not a pointer type anymore. But when I look at this hex representation, it's pretty much the same thing, right? The value is the same, but it doesn't matter if I interpret it as a long pointer or a long integer. Doesn't matter, the value is the same. And then this free memory says freeing memory at address this. So I allocated 10 bytes and then freed the memory, right? So in test 3, what I'm doing here, I'm using the unsafe class and allocating 100 bytes. So 100 bytes of memory. And this returns a pointer base or a pointer, a 64-bit integer that is basically the address of the beginning of that memory block. I call it pointer base, right? We have to have a record of this so that we can access different blocks or different parts of this memory block. And I'm just again converting to hex and then looking at its value. So let's run test 3. And obviously I then need to free the memory, but I have to pass the address of the beginning of the memory block. That's why I need to save this pointer base and make sure that when I call the free memory, I use this the base pointer, the pointer that is pointing to the beginning of the memory block. So if I run this, again allocating 100 bytes of native memory at this address, and then this is the long integer in Java, which is the same value. So I have a correct pointer or a correct integer that is the address of the memory block, and then I free the memory at this address. All right, now let's work with primitives. Let's say I want to put a integer inside this array. Now obviously I have the address to the beginning, so I can start populating or putting values in this 100 bytes of memory starting from the beginning. So how do I do that? So I have this native method putInt. I give it the address at which I want to put this integer, and also have this getInt. I give it the address at which it should return read the value and return it to me as integer. So note what happens. So we give it some address, and then we know that this is a byte array. It's array of bytes, and integer is 4 bytes. So integer is 4 bytes. So it starts populating, basically it starts from this address and goes 4 bytes and puts this value inside those 4 bytes, right? So if I want then to put another integer, I have to take this address and increase it by 4 bytes. Note that I'm doing the memory management by myself, all right? So how do we implement this in C++? It's very easy. PutInt. We have this JLong address and JInt. So I convert this address to a pointer address that points to an integer, right? And then so I take this address, which is a 64-bit, I convert it to a JInt pointer, and note that this doesn't this doesn't make address a 32-bit value. Remember, pointers are 64-bit on a 64-bit platform. It doesn't matter if it's a pointer to a JInt or a pointer to short byte, whatever, doesn't matter. It doesn't, when we typecast a pointer to another pointer type, it's just the way we interpret it. And note that I'm using SC style casting. So I'm saying that this is a memory address, but right now it's an integer. Its representation is a 64-bit integer. So convert it to a pointer type that is pointing to a JInt, right? And then if I want to put integer at that address, JInt, I dereference now this pointer and set the value to X, right? So what happens here? Because now the type is JInt pointer, it knows that if I put JInt, when I dereference it, I'm allowed to assign the value at that memory address to any JInt, because the type of this pointer is now JInt pointer. Now you can imagine what happens for double, float, whatever. We take this address, we convert it to a pointer type that we want, and then we dereference it and assign it the value. So this is put int, right? We take the JLang, the integer address, and then convert it to the pointer type that we want, and we dereference it and assign it the value. The get int is easier actually. So basically we send the address, and then again we convert it to a type that we want. Here, because I want an integer, I convert it to JInt pointer. And when I dereference it, the compiler knows that because this is pointing to an integer JInt, it has to read 4 bytes starting from this memory address. That's why we do this casting, so that compiler knows how many bytes to read from this memory, starting from this memory address. It knows that because this is pointing to a JInt, it has to read 4 bytes. So we just convert this integer address 64-bit to a JInt pointer and dereference it. It knows that it has to read a JInt, so we directly dereference it and return the value. Okay, so let's look at our basically example here. So if when I allocate this 100 bytes, I get this pointer base. I call it pointer base. It's a 64-bit address, and it's pointing to the beginning of the memory block. And I said, okay, put unsafe.put int, start from this address and put an integer. And remember, this populates 4 bytes because integer is 4 bytes. And then if I want to retrieve it, I say unsafe get int, and I have to give the memory address the start point from which I want to read. So here, this is the, let's say if I want integer is 4 bytes, so I want to read 4 bytes. So I have to give the address of the first byte, and it automatically from that it knows that it has to read 4 bytes. So if I run this, so as you can see, I was able to put this integer into this memory address, and I was able to retrieve it 1, 2, 3 correctly. All right. And then what about, so this is another example. Let's say I put one integer. Now I want to immediately put another integer. So this is a second integer after the first one, right? How do I do that? I need to say put int, and I have to give the address. So the first integer starting from this pointer occupies 4 bytes, right? So the first available byte, or the first free byte after the first integer, is 4 byte offset. So usually this, we don't hard code this, we use the offset. So basically we can call int or long int offset is 4, right? We define these offsets, and then we say that go 1 integer from the base pointer, go 1 integer and put this value, right? And then again from and if I want to retrieve the second integer, I have to say that the base pointer plus int offset, because I originally put 1 integer, so I have to advance 4 bytes, right? The int offset is 4 byte. I can also other types like the double offset. So double offset, double is 8 byte. So I can also have this. So if I run this, I should be able to put this 123 in this memory address and then successfully retrieve it. And then I put 222 in the second memory block or the second memory address, which is 4 byte offset from the original integer, and I should be able to successfully read it. As you can see, this is the first integer and this is the second integer, and these two integers are put exactly next to each other in the memory block that I reserved, this 100 bytes. All right. What about doubles? So I have the double is 8 bytes, so double is 8 bytes. And then we put double at some memory address in our allocated memory block, and then double value, it doesn't return anything. And then when we get double, we pass in the beginning of that 8 bytes, the first byte of that 8 byte, we pass the address and it returns a double. So in the C++, pretty much the same thing. Put double, this is our address, which is a 64-bit integer. We convert it to a J double pointer, right? It doesn't change the value of the address. So this pointer, the value, the 64 bits of this pointer variable is exactly the same as this JLang variable address. We're just reinterpreting what it means. It's a J double pointer. Now if I want to put this J double, I dereference this pointer. And now compiler knows that because of this typecast, this pointer is pointing to a J double block or 8 bytes in the memory. And I can dereference it and assign it to a J double, which is 8 bytes. And the compiler knows that, okay, I have to go to this memory address and write this 8 bytes of data into this memory. And how do I do the get double? Again, we pass in JLang address. So we convert it to a J double pointer because we want to retrieve a J double, and then we dereference it. And what this tells the compiler to do is that compiler says, okay, this pointer is a memory address which is pointing to a J double, so I have to go that to memory address and read 8 bytes and then interpret it as a J double. That's exactly what happens. I go this pointer memory address and then dereference it, it returns a J double, and I send it to Java. All right, so this is how we work, how we can immediately or quickly use JNI to implement an unsafe class for ourselves. It's extremely easy because JNI is extremely easy to use. JNI is the easiest native interface any programming language could have, right? So working with doubles, so I put two integers, right? Each integer has an offset of 4 bytes, so 2 int offset. This is the beginning of the available memory bytes for me, and I'm putting a double value minus 12.33. And then if I want to get double, again, I have to go to the beginning of this, the beginning memory address for this 8 bytes, right? So this is 8 bytes, which is a double value. So my base, the pointer or the memory address of the 8 bytes that correspond to this double number is pointer base plus 2 integer offsets. All right, and then I should be able to retrieve this value correctly, and as you can see, I can retrieve it. So let's do one more double here. Let's say 101.05, and then I put 2 integers, so I offset the base pointer by 2 integer offset, plus now I also add a double offset, because I also added a double offset to my I added a double variable to my memory block. So we can basically put these inside our basically unsafe class, these offsets. What is the offset for an integer, a double? But then this memory management is manual, which means we have to remember where each value begins. For example, this value begins at an offset 2 integer offset plus a double offset, because we have already put 2 integers and 1 double inside our memory block. All right, so variable 4 and then var4, so we should be able to put this on our native memory block and then retrieve it. All right, so let's see. And as you can see, we are able to correctly retrieve it. Now obviously, if we go beyond the bounds, let's say we only allocate 10 bytes. So first integer is 4 bytes, the second integer is 4 bytes, 8. The first double goes beyond the 10 bytes. So we are corrupting the native memory. But then here it works still fine because apparently there is no other process that is using that memory. But we have to be careful to never, it's a very dangerous thing to go beyond the bytes, right? All right, so let's do one more. So here we can also look at other types, for example, float or double. But again, the process is very simple. We have to, when we have this JLang address, we cast it to the type that we want, and then basically we dereference it and get the value or add the value. So this is float, which is 4 bytes. So float is 4 bytes. So this is get float and put float. And then we select our unsafe class and run Java H to update the header file. And now we have the get float and put float. And then we go to the CPP and quickly provide an implementation. JNI environment is the JVM. So let's copy this here. J class is the calling class because it's a static method underscore class. And JLang is our address that we are putting. This is pointing to the first byte of the 4 bytes that we are going to read to write from, right? So JFloat, and here what we're going to do is we're taking this address, all right? And then it's a 64-bit and we want to cast it to the type JFloat pointer, all right? So JFloat pointer is so we're just telling the compiler to reinterpret this integer 64-bit integer as a pointer to some float, and now we can dereference it and assign it to a JFloat. That's how we put a value. And then when we read it again, basically the same here, we reinterpret this 64-bit integer as a memory address to a JFloat, and then when we dereference it, the compiler knows that, okay, this is pointing to a JFloat, which is 4 bytes, so I have to start from this address and read 4 bytes. All right, okay? So this is how we can quickly implement these unsafe methods. And then now we copy and paste the dynamic library back. And then let's go to our test unsafe class, and let's create an offset for a float. So float offset is 4 bytes. All right. So let's copy and paste these. So var5, in the var5 we have already put 2 integers and 2 doubles, right? 2 double offset, and let's say minus 2.5 float. So 4 bytes for the float value. All right. And then so 2 integer offsets plus 2 double offsets. This is the beginning of the 4 bytes of memory block for this float value. So we should be able to retrieve this float value with no problem. So let's run this. And as you can see, we are retrieving this minus 2.5. And I should basically return this back to 100. So let's run this. And this is how we can basically work with the unsafe class. Now, as I mentioned, the JDK has the unsafe class. It's in the sun misc package, sun misc unsafe. We always put the unsafe inside the misc, right? So it's an unsafe class built into the JDK, and again, it provides us all these methods. For example, it provides us 2 types of methods. One that allows us to allocate memory and then work with primitive types. And again, this is good when we want to have a class that has different types of arrays, but we want them to be in a contiguous part of the memory because we want to increase the locality of the memory. So we have get byte that we give it a long integer for as an address, exactly what we talked. And then Put byte, long, the first parameter is long, which is the address, and the byte is the value of the byte. Get short at this memory address. Put short, the long, the first argument is the long, which is the memory address. The second argument is short, which is the actual value. Get char, put char, get int, put int, get long, put long, get float, put float. And again, the first parameter is a long integer, 64-bit integer, which is the memory address. When we go to the native code with C++, we reinterpret it as a pointer to whatever the type is. So if, for example, in the put float, we reinterpret this long integer as a JFloat pointer, exactly as I showed you. Get double, put double, get address, put address, allocate memory long. This long is the number of bytes that we want to allocate. Reallocate memory, set memory. So this reallocate memory, I think the way it does is that it takes the beginning pointer, the pointer to the beginning of the previously allocated block, and the second one is the new size. So it deletes the previous array and then allocates from that original base pointer with the new size, right? Set memory, set memory. This for example, this set memory allocates a block of memory, and then each piece is 1 byte, and you can basically put this value of byte inside every single byte. This is equivalent to calloc in C, for example. It allocates and it also puts the amount that we specify in the calloc function in each byte. Copy memory, we can use the memcopy, memcpy in the C++ to basically use this copy. And free memory, again, we pass in this long integer, which is a pointer to the beginning of the memory block, and it calls the free function or the delete array function. So the second set of functions for the Unsafe Unsafe is working with objects. So get int object long, basically it says that, okay, go to this object on the which is on Java heap, and at this address, basically this long is the address to the integer field of this object class. So here we are directly getting a integer or different types of fields inside an object if we know the address, right? So get int, get object, get boolean, object, long, these are the address of these boolean fields, etc., right? So the Unsafe Unsafe provides low-level memory address. We need to use reflections to get access to it, and again, because it checks the class loader, the loader of the class that is calling it, and if it's not part of the bootstrap classes, it doesn't allow you to access it. It's a single tone. The field, the instance is the unsafe, the name, right? And then again, the way we access it is we say class.forName Unsafe, because this is part of the bootstrap classes, so it's definitely on the class path when we run the JVM. And then we say get declared field the unsafe, and then it's a private, so we set accessible to true, and then we can get it. It returns an object, and then typecast it to the unsafe, and now we have full access to the unsafe, right? So if you want to use the Unsafe Unsafe, just use this reflection approach. So I hope you enjoyed this lecture. Now you have a very solid understanding how to do manual memory arrangement or manual memory allocation and management in Java. Please stay tuned, and I'll see you in the next one.